All right, guys. Question on the homework before we get started.
Oh, yeah. What did I miss?
Thursday.
Thursday? No. Wednesday, Tuesday, Wednesday, Thursday. And I was knocking off 3 of those days. I've already had a reason, bro. It looks hard, but it's all on the same, like, intelligence level. What hour do you have?
All right. So, simplest form. We talked about this Thursday. So, radicals are the expressions are considered to be in simplest form if no radicals have perfect nth powers as factors other than 1. Really, that's saying we can't leave something as, say, the square root of 8. Because the square root of 8, we have 4 times 2. Square root of 4 is 2. We can simplify it. If there is a number or a product or term inside the radical that can be simplified out, we need to simplify. No radicals can contain fractions. We can't leave it as the cubed root of 2/7. We cannot have a fraction inside the radical. And lastly, radicals cannot appear in the denominator. We can't leave something as 1 over 3 plus square root of 7. Can't have radicals in the bottom of the fraction, be it 1 or an expression. So when we're looking at these here, we're simplifying them down as far as possible, making sure there's no perfect nth powers, there's no term we can reduce out, no fractions inside the radical, and no fractions on the radicals on the bottom. So even 1 over the square root of 7, we cannot leave it in this form. Now there's 2 main properties we'll use today, the product property with radicals. Product property says if we have 2 things being multiplied inside the radical, we can rewrite it as 2 radicals being multiplied together. Or we could go the other direction, and if we have 2 radicals being multiplied together with the same index, we can write it as a single radical with what's inside being multiplied. Our quotient property tells us that the nth root of a divided by b is the same as the nth root of a over the nth root of b. Or if we have 2 radicals being divided with the same index, we can rewrite it as a single radical. The reason we would rewrite it as a single radical is what's inside each of those radicals. Those numbers are divisible. We can divide them out nicely. Simplifies nicely. So, and a lot of what we're doing in the rest of Phi 2 is really doing a lot of simplifying these radicals so that they are in simplest form or a little bit nicer to work with. Now some, like the first few here, we could type these into the calculator and it would tell us the answer. But the 30xs with non-square roots, so these cubed roots, 4th roots, 5th roots going up, if it does not simplify completely, it's going to give you a decimal answer. It's not going to tell you what it is in simplest radical form like it would with square roots. So we actually need to know how to do these and kind of break them down. Because with our first one here, the cubed root of 12 times the cubed root of 18, we're looking for what number times itself 3 times would give us 12 or give us 18. And one of the easiest ways to find that is our factor trees. Because 12, we can say is 2 times 6. And 6 is 2 times 3. So our prime factors are 2, 2, and 3. So we can say 12 is 2 squared times 3. We'll write that in here. Well, we can't take the cubed root of 2 squared because, again, we need something times itself 3 times. That doesn't work. We only have 2 2's. 3, we only have 1. So we can't simplify anything with that there. Now, if we look at 18 as a factor tree for our factors, again, we have 2, and this time it's times 9, and 9 is 3 times 3. So 18's prime factorization would be 2 times 3 squared. But with 18, we only have 2 to the first and 3 squared. We don't have enough 2's or 3's in either one to take the cubed root of it. But according to our product property, if we have 2 radicals being multiplied together with the same index, we do, 3 and 3, we can multiply our terms inside. So our 2 squared times 3 is going to be multiplied with our 2 times 3 squared. And when we multiply like bases, we can add the exponent. So our 2 squared times 2 would be 2 cubed. Our 3 times 3 squared would be 3 cubed. So individually, we could not take a cubed root of either one, but when we multiply together, we now have 2 cubed times 3 cubed. Can we take the cubed root of 2 to the third power? Yes, and we can take the cubed root of 3 to the third. Now, we don't necessarily have to write this step out, but I'm redoing the product property, simplifying those, splitting them back apart so we can see. Because we do have 2 things still being multiplied together inside the radical. We can split it as 2 radicals. And the cubed root of 2 to the third would be 2. The cubed root of 3 to the third would be 3, and 2 times 3 is. So the whole goal is to find these perfect nth roots that we can pull out. So for cubed roots, we're looking for groups of 3 of that term. So 3 2's being multiplied together, or 3 3's being multiplied together. If it had been fourth roots, we'd be looking for groups of multiples of 4, 4 2's, 4 3's, 4 of whatever number being multiplied together or variable. Well, here, the cubed root of 12 times the cubed root of 18 is 6. Questions on this here? Let's look at the next one, the fourth root of 80 divided by the fourth root of 5. One, we need to get the radical out of the bottom of that fraction, and then we need to make sure that there's nothing that simplifies from there. Now, one thing that would be nice is if 80 and 5, if 80 divided by 5 nicely. Well, yes, 80 is a factor, or 5 is a factor of 80. So using this property of radicals, 5. We have 2 radicals being divided by each other with the same index. We can write it as 1 radical with what's inside being divided. So the fourth root of 80 divided by the fourth root of 5, that should be a 4, not a 5, will give us the fourth root of 80 divided by 5. Well, at this point, we can divide 80 by 5. And 80 divided by 5 is not 5. That would be 25. Because 80 divided by 5 would give us 32. So we do this especially if those two numbers, the number inside the radical on top is divisible by the number inside the radical on bottom, because it simplifies out. Yes, sir. Okay. Yeah, no, that makes more sense. That would actually work out better. Thank you. Yeah, 16. Yeah, it is. 8 by 5. It is 16. Thank you, sir. Yeah. Because that would have given us the wrong answer. But it's 16, yes. Thank you. Questions on this so far? All right, questions on this here? Now we need to see if we can take the fourth root of 16. If we can, we need to simplify it. Now 16, if we do factor trees, smallest prime number that goes into 16 is 2, and it'd be 2 times 8. 8 is 2 times 4, and 4 is, how many 2's do we have? So 16 is the same as 2 to the 4th power. And we're taking the fourth root of 16. We're looking for a number times itself 4 times. So what would the fourth root of 16 be? So we can say the fourth root of 2 to the 4th, which is indeed 2. And that's it. Actually, we have the cubed root of 4 times the cubed root of 128. Cubed root of 4, we can't take the cubed root of it directly, because 4, as we've seen, as we know, is the same as 2 squared. So that's, we don't have enough 2's to take the cubed root of it. Now the other one we're going to look at is 128. Well, 2 is a factor of 128. It would be 2 and 64. 64 does have a factor of 2. It would be 2 and 32. 32 would be 2 and 16 is 2 and 8 is 4, and 4 is 1, 2, 3, 4, 5, 6, 7. So 128 is 2 to the 7th. Now there's different ways we can go from here. We can simplify the cubed root of 2 to the 7th. Because again, we're looking for groups of 3 2's. Do we have more than 3 groups of 3 2's in our cubed root of 2 to the 7th? Yeah. And at this point, we can simplify it and see where we get. Or we can multiply them together. Because if we go on and just multiply them, multiply these two here, we'd be talking about the cubed root of 2 squared times 2 to the 7th. Multiply like bases, we add the exponent. So our 2 plus 7 would give us 2 to the 9. Now, here, we can't just cross the cubed root of 9 out, because, well, the main reason we can do that is if they are both the same, the cubed root and the third power. Now, again, when we take the cubed root, we're looking what? How many times the number is multiplied by itself in this case? 3 times, yes? Well, we do have that. How many times, how many groups of 3 2's do we have here? 3. Because 9 is 3 times 3 times 3. Now we can look at it in one way, because 2 to the 9th is the same as 2 to the 3rd, times 2 to the 3rd times 2 to the 3rd. And each one of these would come out of the radical, leaving us with 2 times 2 times 2, or 2 times 2 is 4, times 2 is 8. Because we could rewrite each one of those as the cubed root of 2 to the 3rd, times the cubed root of 2 to the 3rd, times the cubed root of 2 to the 3rd, which would give us our 2 times 2 times 2, which is 8. Because this is just our product power of product. Yes. Now, powers of powers, multiply. I mean, 2 to the ninth is the same as 2 to the third, powers of powers. Well, this and the outer one would simplify, leaving us with 2 to the third, which is 8. There's just different ways we can go about simplifying them, but in either case, we have 3 2's that are going to come out of this here. Questions on this here? And the last way that we can do this, I've written this a few times, the nth root of a to the x is the same as a to the x over n, yes? So as a rational exponent, our n, the number on bottom would be 3. The number on top would be 9. Well, 9 divided by 3 is 3. And 2 to the third is still 8. There's multiple ways for us to simplify from here. It's just figuring out which one we want to do. Questions on this here? Let's look at the next one, the fifth root of 192 divided by the fifth root of 6. Does 192 divide by 6 nicely? 192 over 6 is 32. So 192 does divide by 6 nicely. So we could rewrite it as a single radical with what's inside being divided. Then we would divide 192 by 6, we get 32. All right, guys, focus in. Now we need to see what number times itself, if there is a number times itself 5 times. That gives us 32. Well, 32 is 2 times 16. 16 is 2 times 8. 8 is 2 times 4, and 4 is 1, 2, 3, 4. Now, if, say, we had 6 2's left over, most likely we wouldn't. One of them would have to stay inside because we can only take out 5 groups of 2. Anything over that has to stay. Does that make sense? So the fifth root of, say, 64 would be 2 fifth roots of 2. We have 1, 2 too many. Questions on these here? Because all these here, because we did get a nice number, the graph or the 30xs, and really the graphing, both of these will simplify just fine. Now when we look at these next two, the cubed root of 135. Cubed root 135. It's going to give us a decimal. Unlike the last one, which was the fifth root of 192. 92 over the fifth root of 6, where it gave us a nice number. It's not going to reduce it. It doesn't reduce our non-square root radicals. So this one here, we do have to do the factor tree of 135. Well, prime numbers that go into 135, well, we know 2 won't because it's not an even number. But it does end in a 5. So it has to be divisible by 5. It would be 5 and 27. 27 is not divisible by 2. It would be 3 times 9, and 9 is 3 times 3. So 135 is 3 cubed times 5. It's all about breaking these into this prime factorization and looking at our groups. So 135, we could say, is 3 to the third power times 5, or we're looking at the cubed root of 3 cubed times 5. Now again, we don't necessarily have to, but I'm going to write this out so we can see this. Because since we do have two things being multiplied together inside the radical, we can break it apart. Well, what would the cubed root of 3 cubed be? Well, the cubed root of 3 cubed is 3. Can I take the cubed root of 5? Well, no, we only have 1 5. So I was going to say the cubed root of 5. And that's it. Because we can take out all the terms, all the whole groups of that radical that we can. Any that we can't, we leave. So even if it had been, say, 5 squared, we rewrote. If it had been, say, 5 squared, we can't take that group of 5s out because we don't have enough. We need group 3 of them. Well, 5 times 5 is what? 25. Instead of leaving it just 5 squared, we'll rewrite it back as 25. We'll simplify where we need. But here we just had 5, so it's 3 cubed roots of 5. That's it. Questions on this one here? Our next one is the 5th root of 7 over the 5th root of 8. Does 7 divide by 8 nicely? No. So our previous method of doing this, making it into 1, dividing, simplifying, is not going to work. But we cannot have a radical in the bottom of the fraction. So the other question is, can I take the 5th root of 8? Well, 8, let's see what it is as a factors. Well, 8 is 2 times 4. 4 is 2 times 2, telling us 8 is 2 to the 3rd. Do I have enough factors of 2 and 8 to take the 5th root? Well, no. So what we're going to have to do is we're going to have to multiply it by something. In order to get, and what our goal would be, is to be able to multiply this by something so that what's on bottom becomes the 5th root of 2 to the 5th. Because if I'm able to get that exponent to be 5 or a multiple of 5, that exponent and that radical would reduce. Because if we look at this here, we have 2 to the 3rd. And if it was, say, 2 to the 5th, that would simplify out. We can take a group of 2's out. Or if we had, say, 2 to the 10th or 2 to the 15th, any group or 5 in that exponent, as long as the exponent is multiple of 5, we can reduce that radical and that exponent. But for this one here, we have 2 to the 3rd. How many more 2's do we need to get, say, 2 to the 5th? 2. Well, we can do this because I can multiply the bottom of this fraction by the 5th root of 2 squared. Because the 5th root of 2 cubed times the 5th root of 2 squared, since we're multiplying like radicals, we'll multiply what's inside. They're really saying 2 squared times 2 cubed, which would indeed be 2 to the 5th. But the only way we can do this is if we also multiply the top by the 5th root of 2 squared. Because the 5th root of 2 squared divided by the 5th root of 2 squared is what? 1. So really, what are we multiplying this fraction by? 1. It's a fancy version of 1, but it's just 1. We're not actually changing its value. We're just changing how it looks. Now the denominator, yes, the 5th root of 2 cubed times the 5th root of 2 squared is indeed the 5th root of 2 to the 5th. Well, the 5th root of 2 to the 5th is 2. On top, well, 7 is a prime number, so we have 7 times 2 squared. Well, there's no way to take the 5th root of 7. There's no way to take the 5th root of 2 squared. If it was, we wouldn't have had to multiply by it. So none of that's going to simplify out. That is in simplest form. Just before we call it finished, we are going to have to multiply that out. We can't just leave it as 5 times 2 squared. Or sorry, 7 times 2 squared. Well, 2 squared is 4 times 7 gives us 28. Yes. So the simplified version of the fifth root of 7 over the fifth root of 8 is the fifth root of 28 over 2. 131. 52. But as bad as this might seem, a lot of this is just rewriting, changing powers. It's all based off powers. Let's look at the cubed root of 500. Now, I will give you another alternative to doing the factor trees. Not as, it may or may not be as nice. It'd be nice if you do know all of your perfect cubes. So 1, which doesn't help us, and then 8, 27, 64, because then 125, and going out and dividing those and seeing which one works. Well, probably doing that is just as fast as saying, well, I know 500 is divisible by 2, which is almost 250. 250 is also divisible by 2. Well, 125 is not divisible by 2 or has a factor of 2, but it does have a factor of 5, which would be 5 times 25, and 25 would be 5 times. So 500 is 2 squared times 5 cubed. So it's just breaking this down, which means for us the cubed root of 500 is the same as the cubed root of 2 squared times 5 cubed. Can we take the cubed root of 2 squared? No, because we need how many 2's? 3. We need groups of 3. We don't have it. Can we take the cubed root of 5 cubed? Yeah. Telling us that we have the 5 cubed roots of 2 squared. Well, 2 squared is what? 4. So the cubed root of 500 is the same as 5 cubed roots of 4, or 5 times the cubed root of 4. And there's a nice way to check this, because we can say the cubed root of 500 in the calculator. Doesn't give us the answer, 7.937000526, but that's the decimal approximation. But we said that in its reduced form, it's the same as 5 times the cubed root of 4. Well, okay. Do those give us the same decimal approximation? Therefore, they have the same value. Even though we can't use the calculator to get the answer, we can use the calculator to check it, especially if you're looking back at it and it doesn't feel like it's the right answer. It's a way to check it. Last one of this type are these two types here. We have the fourth root of 19 over the fourth root of 2. Or sorry, 4. Fourth root of 19 over the fourth root of 4. Kind of like the last one, the numerator, 19 is prime. The only numbers that are divisible or factors of 19 are 1 and 19. No other factors. It's prime. Now 4 we can rewrite as what? 2 squared. Now the goal for us is to multiply the top and bottom of this fraction in order to give us the denominator to be the fourth root of 2 to a power that is a multiple of 4. And we want to hit the next multiple of 4 after the power itself. So that way that exponent and that fourth root would cancel. So here the exponent that we had is what? 2. So the next multiple of 4 would be, well, 4 for itself, yes? Now the reason I say multiple is it's not like this here. Let's just say it was the fourth root of 2 to the 5th. 4 would not be the number we're looking for, because we have how many of them? 5. We already have more than 4, but they don't simplify out nicely. What would the next multiple of 4 be? 8. So we'd have to see how many more 2's would get us to 8. Or for past 8, we're not going to 8, we're going to 12 or 16 or going up. Yes. Because again, we need that to simplify. Each group of 4 would simplify. So we would need a multiple of 4 as the exponent. Well, but here they told us it was 2. So our next multiple of 4 would just be 4. So how many 4th roots, what exponent are we going to put each of these to? 2 to the second. Because the 4th root of 2 squared times the 4th root of 2 squared would indeed be the 4th root of 2 to the 4th. And the 4th root of 2 to the 4th is indeed 2. Now, if it had been the 4th root of 2 to the 8, it wouldn't just have given us 2, it would have given us 2 squared because we had 2 groups. On top, we have the 4th root of 19 times 2 to the second. Well, 19 is prime. We can't take a 5th root of it unless we have 5 of them. Or sorry, 4 of them. We only have 1. And 2 squared won't reduce, so we're looking at 19 times 2 squared, or 19 times 4. Which would be the 4th root of 76 over 2. And it feels like the 4th root of 76 should have, or should be able to reduce. It doesn't. Because if it could, the product of those numbers, 19 and 2 squared, would have reduced. But that's it. Questions on this here? Would y'all agree that there's not a lot, but kind of a lot at the same time? It's all about how we think about this. Last thing we have is we want to write these as simplest form, because again, can't have a radical in the bottom of the fraction. Now again, we're going to multiply this by 1, a fancy version of 1, to get the radical to go away. Specifically, we're going to multiply by the conjugate. Now the conjugate of the denominator. So we're still going to have the first term, the 2 terms, 5 and the square root of 3. But the sign in between is going to be flipped. Because y'all should remember this from our chapter with our higher degree polynomial functions and our quadratics. Our complex conjugates, if a plus bi is a solution, a minus bi. Same thing with radicals. Because again, what we want to have happen is that the radicals in the bottom of the fraction go away. And what we're going to do first is we're going to multiply this out. I'm going to focus specifically on the bottom of the fraction first. We'll come back to the top in a minute. When we do this multiplication, well, 5 times 5 is 25. 5 times negative square root of 3 is negative 5 square root of 3. Positive square root of 3 times positive 5 is positive 5 square root of 3. And lastly, square root of 3 times negative square root of 3 would be negative square root of 9. 25. Negative 5 square roots of 3 plus 5 square roots of 3 would be 0. So those radicals go away. Minus, well, we still have this square root of 9 left, yes? Well, what is the square root of 9? So multiplying by that conjugate actually removes every radical from the bottom of the fraction, yes? Okay, now all we have left to do is to multiply the numerators. And then we are done with this problem here. So we're going to multiply through. 1 times 5 is 1 times negative square root of 3.
I don't think you know. I know, but I just want to know. Just in case we ever do go on later. Your best guess.
I don't know if you'd want to pay it.
At least what would
Well, whatever it would be, you'd be very disappointed. Well, what did we just see here? I can do 1 over 5 plus the square root of 3, and we got our... So what could we also do with... Yeah. There's 7. I think it was minus 2, yes? Or we could say 2 plus... Questions on this here? That's it. So 14, 15, 18, 20, then 22 through 28 even, and 31 through 34. Or really, I could have just said 18 through 28 even. Yeah. Yeah, because 18, 20, 22, 24, 26, 28. Yeah.